So this is the first time that we've tried, or I've tried to actually do a YouTube video that I will send you the link, and you can respond and watch the video from there. So today we're going to talk about many different types of questions, but the first question we want to talk about deals with batteries. So if I look at the questions here, it's like, what item of the following list is not part of the normal monthly battery inspection? So to even begin to look at this, we need to understand that I have three different types of battery inspections. I have monthly, I have quarterly, and I have annual. So let's look at what those things are that I might do on a monthly basis. Well, on a monthly basis, I would measure the float voltage at the terminals, not individual cells. I would do a visual inspection, general cleanliness, those sorts of things. I would look at the charger, look at the charger output, both voltage and current. Check the electrolyte levels. In each one of the cells, obviously. Check for cracks in the cells. I would check for corrosion on the battery itself and all connection. I would take the ambient temperature. Check for ventilation too to make sure it's there. Then I would have pilot cells. Now in that pilot cell, I'll take voltage and temperature and specific gravity. So that's voltage, temp, and specific gravity. Then always, anytime I go into a battery room, check for battery grounds. That's a bad thing to have. We can't afford to have that. So check for battery grounds. We don't want any of those. And then we would also note all monitoring systems. So what kind of alarms do they have? Where do they go to? Those sorts of things. So that would be the monthly test. Now the quarterly test would be the monthly test. But in addition to that monthly test, we would do the voltage on all cells. Okay. And we would do the specific gravity on at least 10%. And we would do the temperature on at least 10%. And in an annual, I would do the quarterlies, which includes all the monthlies. But finally, on an annual string, I'll actually do specific gravity on every cell. I'll do connections. All connections will be checked with a digital low resistance ohm meter. And I'll do a cell impedance on each cell. So those are the standards that's put forth by the IEEE guides with regard to battery maintenance. So with that, let's go on here and see what we got. So what item of the following list is not part of the normal monthly battery inspection? Just let her be there. You don't do voltage checks of each individual cells. You only do that on the pilot cells during the monthly inspection. Number 2, a terminal connection resistance of more than so many percent above the installation requires a clean and restrap. Well, that's 20%. But now that requires that you have the historical data from when it was installed. So in the absence of that, you're going to be stuck with 20% of similar type connections, which should basically be them all. Now, when you're doing straps, we need to also take into account that the straps, the inner cell connectors, the inner tier connectors from the top tier to the bottom tier, those straps are a lot longer than just the one cell to the other. So they're going to have a different impedance value there, but all similar should be the same. The individual cell voltage of a lead calcium, if it varies by more than so many volts from the average, the battery system should be equalized charged. Well, that one's a pretty specific one. That's 0.05. Now, normally they're going to ask you about lead calcium batteries. So 0.05 volts would vary. Now, you have to understand that that's from the average voltage. So let's just say that I've got a 60 cell battery and my overall cell voltage is 136 volts. Well, if I take that 60 cells divided by, 136 volts divided by 60 cells, that turns out to be 2.266, 2.27 volts. So if any one of those cells are less than 2.25 or greater than 2.32, then that battery needs to be equalized. Now, looking at the cell here, we'll talk about that in a little bit, but normally we're talking about lead calcium batteries. So let's go on down here. Number 4. What's the typical float voltage for a lead calcium battery? Well, that is 2.24 volts per cell. That's the typical float voltage. So if I go back to my example, 2.24 volts per cell times 60 cells, and this is where it comes into for us to understand a little bit, but that is 134.4 volts. So we would typically call this a 120 volt control battery. Well, it's not a 120 volt control battery. That's what the rated voltage is, but it's going to be operating at 134.4 volts. So we need to be aware of that. That's the lead calcium. Now, if it were lead antimony, another type, lead antimony, that float voltage would be 2.17 volts per cell. But I would imagine that the questions they ask would likely be lead calcium. So an equalized charge for lead calcium battery would be what? At 2.35 volts per cell. That's where we'd equalize it. Do the same math, 2.35 times 60 cells, and that's going to tell us what the overall string voltage needs to be for this battery. It's 141 volts. So if we found a variance and one of the cells were a little low or a little high, then I would set the battery charger for 141 volts, and that would be my equalized charge. Now, important thing here, question number 6. An equalized charge when needed should last for, and it is at least 24 hours, but it does require monitoring. A lot of the battery chargers have a timer on it, so you can set that charge for 24 hours and it turns itself off. But you better be following back up, because if it stays on, you're going to boil all the electrolyte out of all the cells and you're going to destroy a battery. Second thing is you actually want to be watching that cell that's low or that cell that's large and see that, make sure that it is approaching the average, which should be 2.24 volts per cell, or get it within that 0.05 volt range. If it doesn't do that after 24 or 48 hours, we may need to go back and put a single cell charger just on that one battery cell to try to bring it up by itself. Because if it's not taken care of, that voltage variance will continue to increase, which basically means all the other cells will have a little higher voltage, and this will be lower, and the battery capacity will be greatly reduced. All right, let's talk a little bit about motors. So I have a couple questions on motors, and these are both good questions. You have a 5 horsepower induction motor. It's consuming 4 kilowatts of power from the supply. What's the efficiency of this motor? Well, this is going to require some knowledge, and they actually are nice enough to give it to you on the test. they will let you know that there are 746 watts per horsepower. So when I look at this problem, I have a 5 horsepower motor. That's 5 horsepower times 746 watts per horsepower. And when I do the math there, I find out that I've got 3,730 watts. Now, the basic understanding that we need to grasp here is the fact that, you know what? That's how much work is being done. This is the output of the motor. Now, what's the input? 4 kW. So the definition of efficiency, I'll write EFF, sometimes it's written as a funny N, it's not a omega, is what? Out over in times 100%. So I've got 3,730 divided by 5,000 times 100%, and I find out that this motor is 93% efficient. So that's an efficiency problem. Good question, and one that's going to be asked quite a bit. You're going to see a similar type question on many exams. Number 2, what's the speed of a 2 horsepower, 2 poles per phase, 480 volt, 3-phase delta connected synchronous motor? Well, we want to bring up a couple points here. We need to understand the difference between a synchronous motor and an induction motor. Synchronous motor has to run at a synchronous speed. In other words, that rotor is locked into that rotating magnetic field on the outside and cannot vary anything from whatever that rotating field speed is. An induction motor doesn't have the ability to it has to have the rotating magnetic field on the outside to create a magnetic field on the inside of that rotor. So there's always a slight difference between the field on the outside and the speed of the field on the inside, because there has to be some attraction there. There has to be a difference. If they were totally in sync, there would be no torque available. So for a synchronous motor, it has to operate at synchronous speed. Well, the equation for synchronous speed, NS, is 120 times the frequency over the number of poles. So if I look at this thing, the whole idea here is like the size of the motor doesn't matter, the voltage of the motor, the phase of the motor doesn't matter. The only thing that matters is the number of poles and the frequency of the system. So if I look at this guy, you got 120 times 60 over 2 poles, and so that's 3,600 RPM. So this 2-pole motor will operate at 3,600 RPMs. It cannot operate any faster. It cannot operate any slower. It has to operate at 3,600 RPMs. As a matter of fact, 2 poles per phase, that's the minimum it could be. So the maximum speed on a synchronous motor on a 60-cycle system is 3,600 RPMs. Now, if we had a 4-pole machine, guess what? I just cut it in half. That would be 1,800 RPMs. So that gives you a concept of what we've got. So the only way to change the speed on a synchronous motor is to change the frequency or to change the number of poles. And since it's pretty hard to change the number of poles that are already made inside that motor, the most effective way is to increase or change the frequency. Okay, question number 3. A 3-horsepower, 4-pole induction motor operates at 3% slip on a 60 hertz system. Again, horsepower has nothing to do with it. But what does have to do it, I have a 4-pole machine. It tells me I've got some slip. So it cannot operate at synchronous speed because it's an induction motor. So that's going to be important for us to take into account. So I go back to my synchronous speed equation. NS is 120. The frequency is still 60. Now I have the number of poles as 4, so the synchronous speed for this machine would be 1800 RPMs. But I said we have 3% slip, so 1800 RPMs times 3%, 0.03, is equal to 54 RPMs. So the bottom line is that rotor on the inside of that motor is turning at 54 RPMs slower than the magnetic field in the outside of the motor that's creating all the work and all the motion. Okay, so the actual speed of the motor is 1800 minus 54 equals 1746 RPMs. So in that case, that motor would be operating at 1746 RPMs. All right, let's move on. MTS tables. Some questions regarding the MTS, maintenance standard. So I'm not going to show the tables here. The MTS manual, the NETA manuals are on the Y drive under Public, under Premier University, and you can find all those NETA manuals there. So if you don't have a copy of the NETA maintenance standard, you probably ought to make sure you get a copy, because we're going to talk about some of the things here, but you're going to have to memorize some sections as well. So question number 1 is like you're performing an insulation resistance test on a 5 MVA 4160 to 480 volt transformer, delta Y. You're preparing to perform the high to low. So a hot lead on the high, a return on the low, and I'm guarding the ground. One of the 3 sets of tests that we do on a transformer. What's the DC minimum voltage that you can apply for that test? And I'm going to assume it's an oil-filled transformer. Well, in the maintenance standard, table 100.5 is one that we want to look at quite often. And if I look at that for a 4160 volt transformer, then the minimum voltage that I would apply to that would be 2500 volts. Knowing that's important. They didn't ask what we do here at Premier, they ask what you should be doing, and a minimum of what you should be doing is 2500 volts. And then they ask, what is the minimum acceptable insulation value? Well, it's in that same table, but it tells me that the minimum acceptable value is 1000 megohms. So knowing a few important locations there, like I always try to get 5 kV, I always try to get 15 kV, and always try to get like 480 volts, understanding where those 3 are, because those are the ones that seem reasonable that they could actually ask. Question number 2. The oil result for a 345 kV transformer indicates the interfacial tension is 30 millinewtons per meter. Is this acceptable? Well, we have to look at another table here. This is table 100.4.1. And we look at that table, it's broken down by voltage levels. And if I look at the 345 kV, then I understand that it has to be 32 or better. Now for lower voltage, 15 kV, 34.5, that 30 is going to be fine. But for the higher voltage levels, 32 is required for the interfacial tension. And basically, that whole interfacial tension test is, if this is my beaker full of oil, I see that if I look at it from the side, it's not flat. There's a little curve there on the side, little meniscus it's called. But I actually try to drop a pin in there, and I measure the pressure pushing up on that pin by the interfacial tension of that oil. And that's the test that's run. Number 3, what oil quality screen test is not performed on silicone that is routine on mineral oil? Well, that's the interfacial tension test. You do not run interfacial tension on silicone. What maximum DC voltage would be applied to a 15 kV 500 MCM cable with 133% insulation? Well, that's a table that I really hated. It's 100.6.1. And it's one that I looked at in the parking lot before I went in and took the test, because it gives us different values for different size cables, different voltage cables, and different percent insulation. And they expect you to know some of those sometimes. I had a couple questions in a couple of my exams. But the bottom line here is for that situation, it's 20 kV. Now, switching away from transformers and cables, let's look at a circuit breaker. So now I'm looking at low voltage, non-adjustable circuit breakers. What's the trip tolerance for that? Well, that's table 100.8. And that trip tolerance is plus or minus 25%. Pretty sloppy. That was just eye-opening to me that kind of range was acceptable. Question number 6. What would be the minimum accepted insulation resistance for a 4160 volt motor that was manufactured in 1968? Well, you need to look at those tables because that's table 100.11. And understand that out of all the items that the maintenance standard covers, motors, there's two different standards. One for prior to a certain year, one after a certain year. So that's table 100.11. And bottom line is for that motor, 5 mega ohms is the minimum insulation resistance value that's acceptable. All right, let's move on. Talk a little bit about power triangles. So consider the power triangle of watts, which is power, VARs, which is voltamperes, and reactive and voltamperes. If the cosine increases, what effect does that have on the power triangle? I never did like this question. I know what their answer is. So here's my watts. Here's my voltamperes reactive. That's my VARs. And here's my voltamperes. This is the angle theta. And cosine of theta is the power factor. Okay? I want you to know it has to be less than or equal to 1. Anything greater than 1 is not possible for a power factor. Okay? So basically what I'm saying is if the cosine increases, what does the effect have on the power triangle? If the cosine increases, if the cosine goes up, I need to understand that the angle goes down. Okay? So if I look at my calculator, I understand that the cosine of 0 degrees is 1, and the cosine of 90 degrees is 0. So this angle, as the cosine increases, this angle theta gets smaller and smaller and smaller. Now, I don't like the question because in my mind, I really didn't change the watts because that's the work being done. But as the angle decreases, the angle decreases, this is my watts, this is my voltamperes, and this is my VARs. What happened? The VARs got smaller, the voltamperes got smaller, and the watts stayed the same. That's none of my choices, okay? What they are assuming is that when this angle got smaller, that they increased the load. So basically the voltampere stayed the same. Basically the current stayed the same. So if that voltamperes and the voltage stay the same and it decreases, then in fact the watts will increase. But in my real world, when the watts are there, that's how much work you're doing, and it doesn't change regardless of what the angle is. That's just what you can do. Question number 2 when it comes to power triangles. Given a power triangle where watts equals 300 watts, VARs equal 400 VARs, determine the voltamperes, what the power factor is. What's the angle between the voltage and current? So I'm going to go to a free page here, and I'm going to start all over again. So I've got 300 watts, and I've got 400 VARs. So the first question is what's my voltamperes? Well, I can use Pythagorean's theorem. I know that the voltamperes is equal to 300 squared plus 400 squared. And so the voltamperes is equal to the square root of 300 squared plus 400 squared. And so that equals 500. So my voltamperes for this power triangle is 500 voltamperes. 300 watts, 400 vars, 500 voltamperes. Well, question number 2 is, what's the power factor? Well, power factor is the cosine of this angle. And the cosine of this angle is always watts over VA, which is 300 divided by 500 is equal to 0.866. So the power factor of this system is 0.866. Well, question 3 is, what's the angle? Well, the angle is equal to the inverse cosine of 0.866 equals 53 degrees. So those are the first 3 questions. Now, question number 4 here. Determine the new power triangle if the angle between the voltage and current were to become 30 degrees. Okay, 30 degrees. Okay. I'm sorry, I made a big mistake here. This is 0.5, or 0.6. 0.6 is 53 degrees. I don't know. I misread my notes. So cosine is 300 over 500 is 0.6. Arc cosine of 0.6 is 53 degrees. So question number 4. Determine a new power triangle if the angle between the voltage and the current is 30 degrees. So let's look at that. Cosine of 30 degrees, that's for my, I got my number, is 0.866. So that means watts divided by voltamperes equals 0.866. So how do I get there? Voltamperes is equal to 300 watts divided by 0.866. And so when I do that math, 300 divided by 0.866 is 346 voltamperes. So I have 346 voltamperes. So my power triangle now looks like 300, 346, and unknown. But I know that that unknown, vars, is equal to the square root of 346 squared minus 300 squared. And when I crunch out the numbers for those vars, they turn out to be 250. So that's my new power triangle. Being able to delve back and forth and angling with those things, that's going to be pretty important for you on the test. Okay, final question. Test calculations. This is an actual example of a problem that was on there about a year ago. So I have this bus bar that's 15 microohms and a similar bus bar that's also 15 microohms, and they're connected together with 2 straps. And the straps are 10 microohms each and have a connection here on each side. So if I look at this strap plus connections, I've got 10 plus 5 plus 5 is equal to 20 microohms. So if I'm going to redraw this, I'm going to redraw this as a circuit. It's like basically I got a little resistor here, and then I have 2 parallel resistors that are my straps. and then the other resistor here. So I've got 15 microohms here, and I've got 15 microohms here, and I've got 20 and 20. These two guys are a parallel circuit. That end result, what's the combination of two parallel resistors? It's the product over the sum. So that's 20 times 20 over 20 plus 20. That's 400 divided by 40 equals 10 microohms. So this entire circuit is 15 plus 10 plus 15 is 40 microohms. All righty. So hopefully that makes sense. If you have any questions, you can certainly give me a call or email me. I do want you to send me an email letting me know that you did, in fact, watch this video so that I can keep attendance records. I appreciate your attention. Good luck. Thank you.